So one of the things I noticed in one of my other classes, or some of my other classes, is that sometimes people don't bring calculators to class. And then I get emails asking for examples of something. And I'm like, well, what about the one we did in class? They're like, oh, I didn't have my calculator that day. So please bring your calculator each day, just in case you need it. I mean, we might not need it every day, but it's helpful. For those of you who have become experts in using your laptop or your phone, awesome. It's just whatever type of calculator you are good at using, make sure you have access to it. Okay, let's pull up these assignments real quick. Give me messages. Sorry about that. I should have had this already pulled up. I explained this in the last video, but I just want to make sure that we are all aware of the timing of when things will happen. Also, please, if you have not, check out that previous video over forces and friction. I gave a lot of information. I kind of just shoved stuff in as quickly as possible. So your projectile motion assignment was due this day. I'm going to check back on all my emails, see if there are any questions that I didn't answer before it was submitted. Like I said, I'm going to be slightly softer grading it just because it was such a mess during the time when we were supposed to learn about it with ice and things. Your forces assignment is due during spring break, but feel free to get it done before then. It's not as challenging as the projectile motion assignment, so please take a look at it after watching Tuesday's video. And of course, if you have questions, email me. So we do have a test coming up. This is how the test is going to work. The test will become available for you either Sunday or Monday, right? Now, I don't necessarily expect you to work on it during spring break if you don't want to. So it won't be due until the 16th, which is the Tuesday we come back. So you'll have over a week to do it. So feel free to take this week off and then do it this day. However, I will be grading whoever has turned them in on this day, the 12th. I'm going to set it up for 2 attempts. So if you want to do it when it pops up, I'll grade it this day, and then you can do it again. Awesome. Right? So we'll have 2 attempts. So if you do it and you're like, oh, I didn't do very well, feel free to do it again. But if you submit it after this day, I won't have a chance to grade, or I won't be grading any from here to like here. So once it becomes available, do it if you want. I'll give you feedback. If you made a good grade, awesome. If not, just try it again. Yes, sir.
Is that just projectile motion, or does it also include forces?
It will include forces. One good thing about taking the test at home is feel free to check back to all the videos and examples. The test is nowhere near as challenging as this homework assignment. There are some slightly tricky things, but I think you'll do great on it. Don't worry, try your hardest. If you don't do as well as you wanted to, try it again. Any questions on how that will work? Awesome. I probably should have worn a bigger mask. This one is getting on my nerves. All right. I think we are all right with administrative stuff. Let's talk about momentum. As I remember where buttons are. There it is. All right, everybody's here. Awesome. So the first question says, what quantities are going to combine to create momentum? And since we haven't done an introductory part on this yet, I'm just going to go ahead and let you know that mass and velocity will be combining in order to yield momentum. So this is going to be a completely different quantity that we haven't thought about before. So we're going to combine mass and velocity to make momentum. All right, this question says, when a quantity is conserved, what does that mean? Does anyone know? You use less. Anybody else got a choice? We got one on this. We got the total amount doesn't change. And we're just going to say randomly that someone says we consider a portion of it. So when something is conserved, that means that the amount of it doesn't change. Thank you very much for everyone who is brave enough to give an answer. It means that the amount does not change. Now, often scientifically, you'll hear someone say that it can neither be created nor can it be destroyed. And that's a very long way of going to say that something is conserved, that a quantity is conserved. So the total amount won't change. There will be something that you might think would change it, but if it's a conserved quantity, it will remain the same. Thank you all for answering. Okay, so we're going to do a brief recap. Here's the Strong equation. We all know and love this. We have something moving at a certain velocity and it accelerates for some period of time. We can tell where it's going to end up, of course. If we got something moving at a speed and it accelerates, we can find out how fast it's going to go. Cool. In class on Tuesday, we learned that the sum of forces is equal to the mass times acceleration. Start on this one. Put a star beside it because definitely you want to check the video out for more info. And also, this is not exactly correct. This is an approximation that we're going to use in this class. F equals ma. And that's the sum of forces equals the mass times acceleration. And we also discussed that the force of friction, F sub u, that's the force of friction, is equal to the coefficient of friction times the weight. Again, this is not exactly true. This is an approximation that we're using. So that was first section, Tuesday. Also, in case you're not exactly sure what a force is, a force can simply be defined as something that changes how another thing moves, right? That's just sitting there. Newton's first law says it ain't gonna move unless I make it move. It starts moving. That means a force was applied. Therefore, we know that a force is something that changes how a thing is moving. Also, remember that force comes in, quote unquote, force interaction pairs. When I say force interaction pairs, I mean that in order for a force to act, it must be acting on something. In order for a force to act, it must be acting on something. And something must have caused the force. So we got something causing the force and something being acted upon by the force. And of course, Newton's third law says that if I put a force on something, that thing puts the same force on me in the opposite direction. I push on the wall pushes back on me. That was your bonus question on your first test. Yay. Okay. Coolness. And I don't know if this link works anymore, but it's going to get a little bit more complicated than what we had introduced before. Is this trying to link to Netscape Navigator? No. Okay. I don't know why it doesn't open in like Chrome or whatever. All right, so we got a car crash in slow motion. Notice how the car's just staying there, because it's not going to just start moving. And then, as this thing plays, which is something that it does, okay, well, notice how it hits it. And now things are moving, quote unquote. That poor car in the middle is not having a good day. That car was in neutral, and so now it's going to start rolling. A force has acted on it, causing it to move. Unfortunately, it's moving into the car in front of it. Somebody's not having a good day right now. Right. So I show this just to show that forces might not be quite as straightforward as we were thinking in the first place. For instance, what if a force continues to act? What if it acts through a period of time? So we want to start looking at that. What else can forces do? Okay. So when we talk about momentum, you can tell by the name of it. Momentum sounds like something's moving, right? We're just going to be discussing motion from a force-centered point of view, right? We want to include the forces that are included instead of just talking about the resulting acceleration. Remember, since F equals ma, the acceleration is caused by a force. So instead of looking at the acceleration and how it affects the motion, let's look at the forces and how they affect the motion. Of course, as it says last, you get the same answer either way. Momentum is just going to be another tool in our toolbox. Okay, first question, what do you think? Should momentum be a vector? I see some heads shaking up and down. Sure, right? I would assume it would be a vector, even if I don't know any equations for momentum. I would assume that it would be a vector. It is. All right. So when we write momentum, which is represented by, and you're going to love this one, which is represented by a lowercase p, right? It gets a little arrow over it, telling you that it is a vector. Impulse is the change in momentum. So what do you think? Should impulse also be a vector? Yeah, I mean, if a vector is changing, then the vector must change in a specific direction. So yeah, impulse, which is the change of momentum, should also be a vector. And you're going to love impulse as well. It's a capital J. Yep. I'm assuming they ran out of letters and Greek letters. Okay, so how are we going to solve for momentum? Well, basically, momentum is It equals the mass of the object times the velocity of the object. Momentum equals the mass of the object times the velocity of the object. How big it is and how fast it's going. And also the direction. Real quick, let's talk about units. Mass is kilograms. Velocity is meters per second. But I don't love that unit. Kilogram meters per second. Sure, it's true, but to me, it doesn't really tell me what's happening physically. If I think of it like this, all right. This is the unit of force. It's a Newton, right? A Newton is a kilogram meter per second squared. And we know that a Newton is the unit of force. If I take kilogram meter per second squared and then multiply it by another second, Newton second, then I get the units of momentum. So now I can think of the units of momentum as a Newton second. And I can think of momentum as a force acting through a period of time. So this gives you a whole different way of thinking about momentum. You can think of it as mass times velocity, but you can also think of it as a force acting through a period of time. In fact, if I wanted, oops, not an S. What did I write an S there? Oh, because units. I can say force times time is momentum. That's true. Well, the camera can't see me, but it would be right. If I push this chair with a certain force, it's going to roll. Awesome. However, based on how long I apply that force, the time through which I apply it, will determine the momentum that the chair gains. So a force through a time. Knowing that will help you greatly. Which means we can also say that impulse, which is the change in momentum. We got a few different ways we can write this, right? Impulse is the change in momentum. We can write that as a mass times a change in velocity. And of course, that's assuming that the mass stays the same. Pretty cool. The reason why I keep showing you all these different ways of arranging things is to help build connections in your mind. When you think about forces, oh, it means this about momentum, or oh, it could say this about time. So I want to help build all of these connections in your head. Let's see. I feel like there's something else I want to tell you. All right, I think we're okay right now. There's another organization that I'm going to tell you, but I'll save a little bit for later. This is just another way of writing F equals ma. Since acceleration is the change in velocity over the change in time. So this is just me like writing it out for you so you can see it. And writing it out like this, for me, really helps me understand things. So I just wanted to put that out there so you would have it in your notes in case you hadn't already made that connection. All right, we got momentum. We got impulse, which is a change in momentum. Delicious. Questions so far? How y'all feeling? Not too bad, right? Yet. Actually, it might not get bad. I think y'all are going to do great. So when we look at a question that says, what is the momentum of an object with a mass of 2 kilograms and a velocity of 40 meters per second? That way, I have to give it a direction. Now you might think, look at this and think, could it really be that straightforward? It can, and it is. Momentum equals mass times velocity. Oops. Yeah, it was really just 2 times 40. I know you all were waiting for a trick or something, but there is literally no trick. It was just plugging in those values. How y'all feel about that? Pretty good? All right. Sometimes I say, oh yeah, this is easy. But if it's not easy for you, raise your hand and be like, Mr. Palmer, quit assuming that I know it. Teach it to me. Okay. Now this one's a little bit more complicated, but let's go through it. We says, thank you. It says a force of 30,000 newtons is exerted for 4 seconds on a 95,000 kilogram mass. What is the impulse applied to this mass? All right. Oops. Impulse, which is change in momentum, can be thought of as this number. We can also think of it as F times the change in time, right? That would indicate a change in momentum if time is also changing. So we might be able to solve this. So we know the force that's being applied. And we know the time period from 0 seconds to 4 seconds. Anything that I'm missing that you can see? There's nothing that I'm missing. Right? Now you might look at the mass of it and think, well, won't that mass play a part in it? That mass will play a part in how fast it accelerates or the velocity change. But we know the force that's being applied to it, right? We know the force that's being applied to it. So we can just take that, multiply it by the time period, which is 4 seconds, and we'll get our answer. A lot of these questions are just, they're slightly tricky, right? You get information that seems helpful, that is important, but maybe not for a specific part. For a question asking about the impulse, if I know the force applied and the time through which that force was applied, I can find the change in momentum during that time. This says nothing about how the velocity will change. Excuse me. We'll have to solve that next. So yes, you all were correct. The answer was 120,000 kilogram meters per second, or Newton seconds, if you will. Questions about that one? We're doing great. Oh, this one asks about the change in momentum of the mass. Can anyone tell me the answer to this question without doing any math at all?
It's the same.
Correct. Remember, change in momentum is impulse. But now I'm going to mix it up a bit. What is the change in velocity of the mass? Now, this is a bit different. To do this one, we'll start here. Sure. And we'll start here. Right? This just says mass times change in velocity. Instead of mass times velocity, it's mass times change in velocity, because this is a change in momentum. Y'all see that? All right. For my J, we already found that, so I can just shove that value in. $120,000. You got my mass right there. Whoops, why did I put a 6 there? And in here, final velocity, initial velocity. Does anybody know what our initial velocity was? Does it even say? It doesn't. Here's the trick. It doesn't matter. Like, I don't. I'm going to say it's 0. The initial velocity is 0, right? All I have to do is solve for that final velocity there. This is another one of those situations where you can set the initial velocity to 0 if you so choose. Because the amount that the velocity changes is going to be dependent on the force that was applied and the mass of the object. There's another way to do this. If you divide both sides by the 95,000, you get a final velocity of 1.26 meters per second. So this is how much the velocity changed by. I know right now a lot of it might look like you're just plugging and chugging numbers, but I want you to take some time to consider what this all means physically. Physically, we have an object whose momentum is changing by this amount and has this mass. And what we're finding out is how much the velocity changes here. Change in momentum, mass is staying the same. How much will the velocity have to change in order to change that momentum? That's what we just found out. Now, at a point like this, you might start asking yourself questions like, what if that mass would have been larger? Or what if that mass would have been smaller? Would that have affected how much the velocity changed? What if that mass would have been larger? Or what if that mass would have been smaller? Would that have affected the velocity change? And that's a very good question for you to be asking yourself. One of the things you might want to do later is test it out by putting in. Now, yeah, I'm sorry, I forgot to point out, it was 1.26 meters per second. I don't know why I thought everyone just had that already. Sorry about that. Cool. Let's switch up the situation a bit. Now I've got a stationary ball. I like visual aids. There you go. I got a stationary ball. And it weighs 0.25 kilograms. Well, the mass is 0.25 kilograms, but since we're on Earth, we can say that it weighs that amount as well. It acquires a speed of 10 meters per second when hit by a hockey stick. I don't have a hockey stick, but close enough. And the question is, what is the impulse imparted to the ball? So we're asking for this much. Well, you can think of it like this. I'm going to ask you some questions. The ball is stationary. Everyone, please tell me, how much momentum does the ball have while it's stationary? My eyesight sucks. I think someone held up a number. 9. Yes, I agree. If it ain't moving, it ain't got no momentum. That's what's up. Okay, so it has this much when it starts. We're going to call this the P initial. And now, the P final is what we need, right? Because remember, impulse is change in momentum. P2 dubs, you can think of that as P final minus P initial, right? Change in. So if I find the P final, and it started off with 9, I should know how much it changed, because it went from 0 to a higher number. So now we've got a very straightforward way of solving this. Take the mass, my m, its velocity, 2 meters per second. Press enter. This gives me its final momentum, 2.5 Newton. If you write kilogram meters per second, that will help you understand that it's something of that mass moving at, or imagine something at 1 kilogram moving at 2.5 meters per second, or you can imagine something at 2.5 kilograms moving at 1 meter per second. I write it like this just because it helps me connect it to forces, but both of the units are true. It's usually just whatever you're talking about. So this is the final momentum. That means that the change in momentum, or the impulse, must be that same value since it started at 0. So if you're reading a problem, look for stationary, or at rest, or not moving, or still. Anything that tells you that something doesn't have any momentum, because this will save you a lot of headache. One of the problems on the test is pretty lengthy, and the challenging part is catching one of these terms if it's in there. It might not be, but if it is. Questions on this one? A little bit more straightforward than projectile motion. Okay. It's almost time for us to switch gears a little bit. But before we switch gears, let's just try one more. One more, about. All right. We got a 1,000 kilogram car. Accidentally drops from a crane. I don't know how that happened, but it accidentally dropped from a crane and crashed at 30 meters per second to the ground below and comes to an abrupt halt. What impulse acts on the car when it crashes? So we want to find the change in momentum. Pretty straightforward, right? Someone please find for me the momentum of the car at 30 meters per second. Someone please find for me the momentum of the car at 30 meters per second. You got 30,000 kilograms meters per second. Right? That's going to be how much momentum it has when it's falling. So once it hits the ground and stops, say it again. Okay. Once it hits the ground and stops falling, what is the momentum going to be? Right? So what's my change of momentum? Right? Because it has to go from this to 0. So we've got some possible answers. Me, personally, I would say here, right? I would say negative 30,000 kilogram meters per second. However, depending on how I have set up my system, it could just as easily be a positive one. But since momentum and therefore change of momentum are vectors, you want to keep track of what these negatives mean. So I did this one just so I could say it could be either of these two based on how you organize your directions, but be careful. Be careful. The reason why it might be positive is generally people set up as their positive direction, right? And the momentum changes from this amount down to 0, so that would be a positive. Or you could think of it as negative if you think it's moving down this way as a positive momentum. So it's just up to you and how you do it. Just keep it straight, right? One way I usually keep myself from having to write negatives is when I answer stuff, I just write my direction. Right? I write everything as a positive, but also put my direction on there. And that makes it a little easier for me. Questions on that one? Yay! Everybody's doing wonderfully. Okay. Okay, yeah, now I'm going to change gears in a moment. So on this one, last one before we change gears. I got an 80 kilogram dude and his car. So I'm going to draw this one. I can't draw, but you get the point. There's a person in there, right? And they're suddenly accelerated from rest to a speed of 5 meters per second by rear end collision. What's the car behind them? All right. Collision to happen. What we're trying to find is the average force that was exerted on him by the back seat of his car. Now, this is asked in the most complicated way possible. The force exerted on him by the back seat of his car, is just a fancy way of saying the force that's exerted on the car. So the whole car is being pushed forward, which means the whole car is pushing him forward at that same amount, right? So that's just me being hilarious and verbose. So watch out for tricks like that. Okay. How are we going to solve this? Sure. Momentum definitely equals, or sorry, impulse definitely equals the change in momentum. I could just as easily say F times change in time, that's also equal to the impulse, right? But this has more information that we might need. We might be able to find the force. We might be able to find the time. Or, watch this. What if I know you are excited about this. What do you think about that? What if I can put the mass change in velocity and the change in time in there. Remember that last equation I wrote on the other screen? I was like, you all might need this at some point for some reason. Yeah, it's that one. So this whole thing was just a setup and a trick for you to have to use the usual explanation of force. This is basically F equals ma. I just said it in the most roundabout way possible. Because if I take his mass, 80 kilograms, his change in velocity, 5 meters per second, divided by the change in time, that's 0.3, I'm going to get the force. Say 1.33333? I don't disagree with that. I think it seems like it should be bigger. Can I look at your calculator? Oh, what's that? I don't know where I was getting the point from. Did you even say 1 point, or did I just make that up? Yay! Yes, she was absolutely correct. Unfortunately, my inability to hear anything say it was wrong. You're absolutely right. Yes, 1,333 newtons, or 1,333.3 repeating newtons, if you'd like. Not bad, right? So even a question that's as complicated as this one just has a straightforward setup that we can utilize to solve it. When we're looking at the momentum of singular objects, things are pretty straightforward. Questions, concerns, comments, complaints? How y'all feeling? Feeling pretty straightforward? Pretty good? Okay. Remember, if not, just stop me and be like, hey, what's up? Now here's where I get to talk about what I really care about. We learned about momentum. We get it. It makes sense. Awesome. But the real benefit of momentum is the fact that it's a conserved quantity. Meaning that the amount of momentum before a situation must be the amount of momentum after a situation in a closed system, right? A closed system means we have a certain number of objects involved, and that's all that's involved. For instance, car A and car B crash into each other. If they are a closed system, meaning that they're the only two objects interacting, the amount of momentum that they have before will also be the total amount of momentum afterwards. That can be written as the sum of momentums for any number of objects is constant. That's great. That means that our job has become a lot easier. All right, so I have a red ball and blue ball. They're moving towards each other, right? Blue ball has momentum 1, red ball has momentum 2. The sum of the momentums, and I put a little b here, that's the sum of the momentums before they hit each other, equals P1 plus P2. No big deal, nothing crazy. So this is exactly what the last screen said. I just wanted to like draw little things for it. Over there on the right, we've got the red ball and the blue ball, except this is after they have come into contact with each other. They have hit each other, right? But you'll notice that the sum of the momentum after the collision is equal to P1 and P2. And the important thing to remember is that the sum of the momentum before the collision is the same as the sum of the momentum after the collision. That's all I was drawing. Yes, I know we probably already knew that. I just wanted to make sure and clarify. All right. So now I want to talk about some specific types of collisions. And like I said to you all earlier, I'm just going to say the two types and then we're going to move on from there. Let's talk about a perfectly elastic collision. Now, like all of the special circumstances I talk about, this is not something that really can happen. Like a negligible air resistance or frictionless surface or spherical chicken. There's never going to be a perfectly elastic collision. But a perfectly elastic collision is when the two objects they hit each other then bounce off of each other. Just bounce off. That's a perfectly elastic collision. Nothing warps, nothing dents. They just hit each other and then somehow bounce off of each other. You can think of those perpetual motion balls where you take one and you hit it and it goes there. Those are very elastic collisions. Those little metal balls don't compress very much at all, so they just tend to bounce. Which is
So you're talking about when neither object can absorb it.
correct. Right. There's no the energy transfer is perfect, is what's happening here. What makes it perfectly collision. So they just hit each other and then bounce off of. But even objects that do perfectly elastic collisions, most of them compress some and then reform. I don't want to go down that rabbit hole. So just imagine that the two objects bounce off of each other perfectly. Or, I guess, this could still be possible. So I'm going to write a little form for a perfectly elastic collision. Here's two objects, object 1 and object 2. They haven't hit each other, but they both exist. And then they hit each other. And you'll notice, hilariously, it doesn't change. Right? These values might change. This might be the velocity before, this will be a velocity after, and after. But the setup is the same on the left and the right. Mass of 1 times the velocity of 1 plus the mass of 2 plus the velocity of 2 before equals the mass of 1 times the velocity of 1 after plus the mass of 2 times the velocity of 2 after. mv plus mv equals mv plus mv, right? Just understand that this is before and this is after. You'll be surprised how straightforward this is. So straightforward that some of you might be bored. All right, let's get excited about it. Whoa! So when we get a question like this, we got a ball with a certain mass and a certain velocity combining or colliding with a stationary ball. Okay, it's gonna make it a little easier. If the initially stationary ball moves off at a certain speed, what is the new velocity of the first ball? All right, for those of you who can't imagine this, let's see if I can make it happen. Come on, camera, you're gonna come over here. Okay, well, you get the point. This is my stationary ball. This is my ball I'm going to move. Now let's see if I can actually make them hit each other. See if I can hit it hard enough to make it actually roll. I cannot. Well, good enough. I'm going to try one more time. Whatever, I did it. That was my example that I recorded on the camera. So when my boss is like, hey, did you do examples in class? I'd be like, you saw it. The point is, when I hit the first ball, it should have, or the second ball should have started rolling, but the balls are not of the exact masses that we were discussing. However, I still wanted you to be able to see an approximate example of what we're talking about. Pay no attention to that value. All you gotta do is start plugging in values, right? The mass of ball 1. I'm gonna call this one ball 1. 0.5. Moving with a velocity of 3 meters per second. You gotta stop for a second, right? When I say that it's moving at a mass of 3 meters per second, I have now established a direction. The direction that first ball was moving is my positive direction. I could say it's negative, I'm not going to, right? So I'm going to actually put a little arrow here just to show that it's moving to the right. That's whatever direction that is. Plus the mass of the second ball. How fast is the second ball moving? It's stationary, so it has no momentum, right? This turns to 0. 0.6 times 0 equals 0. I'm not even going to waste my time writing it. So all of the momentum that we have comes from that first ball. So this means 1.5 kilogram meters per second. That way, that's all the momentum we're going to have. Y'all see that? No more momentum can pop into the system. All right. Mass of the first ball, 0.5. We don't know this velocity yet because it doesn't tell us. Plus the mass of the second ball, 0.6. And it moves off at a speed of 2 meters per second. The reason why I put this arrow is just to, once again, show you that this ball is moving the same direction that the first one was moving. There's been no direction change here. You don't necessarily have to put all this mess in your notes if you can keep it straight. But me, if I don't put this, I'm going to be like, what was that? Where did that come from? All right. Now we can get to solving. We got 1.5 subtract 0.6 times 2 from both sides. I'm going to have to divide both sides by 0.5. I know I kind of shortcut that. Everybody check it out and make sure you know what I just did. This, back to there. This, divide both sides by. I'm pretty confident in my math. This is my confidence stance. 1.5 minus 0.6 times 2. Woo! What about 0.5? Cha! I'll give you all a second to get an answer in case you hadn't already. Before I shut up, let me make sure and show this again. Got this from both sides. I think everybody got it. I just wanted to show you. All right, what's my answer? I agree. 0.6 meters per second. And this is 0.6 meters per second in the same direction that my initial ball was going. Right? So what this tells me is that after the two balls come in contact, the ball that was not moving gained some velocity, 2 meters per second. And the first ball loses some velocity. If you got super bored, you could check the change in momentum of both of those objects. If you got super bored, you could check the change in momentum of both of those objects, which is what we're going to do right now. Second object, change in momentum was 0.6 times 2. All right, it gained 1.2 kilogram. It gained 1.2 kilogram meters per second in this direction. Okay, that's object 2. Let's find out about the first one. And I'm sure everybody already knows what the answer is going to be, but we're going to act like we don't. Five. 6. Awesome. And this is so weird, right? The first ball, 1.2 kilogram meters per second in the opposite direction. I'm making a giant statement here, right? I'm just not saying it. This one gained an amount of momentum. This one lost that same amount of momentum. I know it seems pretty straightforward, but I want you to like shove that in your heart somewhere so that you always know that. We have two objects coming in, they interact with each other. If one of them gains a certain amount of momentum, the other one must lose that amount of momentum. Goodness, let me write it in another way to hopefully make it. Discussing perfectly elastic collisions, the sum of the change of momentum equals 0. That's another way of saying that it's conserved. That's just another way of saying that the momentum is conserved. If this one loses something, this one gains it, vice versa. Momentum-wise. Question about that. I think the reason I made such a big deal about it is I felt so smart when I was like, oh wow, look at that 0. All right, let's keep going. All right, so let's just say I decided to take my son ice skating. And we've been having a good day skating around. And then we're standing there fixing his little hat or whatever. And then we push off of each other. What can we say about the momentum? Either the father has more momentum, the son has more momentum. They have the both. They have the both. They have the same but opposite momentums, or what do you all think?
Same but opposite.
I hear same but opposite. Anyone vote against that one?
Will the sun have more momentum because he weighs less?
We got the son having more momentum. And nobody else said, okay.
But they're pushing each other, so they get equal force back to each other.
So we got 2 for this one? All right.
3.
There you go. we got 3 for 3. Let's check it out and see if we can find out. Momentum is conserved, so we know that the sum of the change in momentum is 0. We know that we got daddy's momentum change plus kid's momentum change equals 0, right? There are 2 momentums that are changing. We got so mathematically, what we can see is that the 2 momentums afterwards have the same magnitude, but opposite directions. So thank you very much for everyone who was brave enough to answer. I greatly appreciate your participation. What we find is that they both should have the same momentum in opposite directions. Now, let me help you all out a bit. Now, if I start looking at the changes in velocities, now we're going to get some different values, right? Because we know that this mass is much higher than this mass, right? And in order for these to be equal, this change has to be higher than this change in order for them to be equal. So what this means is that whichever one was over here, I put the kid over here, is going to increase in its velocity more because of its smaller mass. So they're going to have the same change in momentum, but not the same acceleration. The less massive one will have the larger change in velocity. Right? Makes sense. Think about it this way. If you'll recall Newton's third law that says when you push on something, it pushes back on you. Now imagine yourself throwing a baseball. You throw that baseball with I don't know pitchers' names, with super baseball pitcher force. Makes it go fast, right? That means the ball is putting that same force back on you, except you don't move, right? You don't go anywhere. But the ball goes flying, right? The ball has a much smaller mass, therefore much greater acceleration. Imagine firing a shotgun. The bullet goes whoochoo, or the shot casing thing goes all out that way, and the gun just kicks back into your left shoulder and bruises it for the next month because you're a kid.
Not if you hold it right.
Not that that was like a memory or anything. And definitely not if you hold it right. I think it's probably an adult's job to say, hey, make sure you don't hold that shotgun incorrectly. Anyway, gun safety. Oh, but yes, they're the same, but opposite momentums. And it relates into real world, so yay. All right, this time we're going to do a slightly different question, but I want you to work on this one yourself using the same process we used last time, except make necessary changes. I'll give you approximately 5 minutes, or 3, however many it takes to work on it, and I'll just sit here. We've got 2 balls moving in opposite directions with velocities of 5 meters per second and 10 meters per second. They collide and move off in opposite directions with new velocities of 7.5 meters per second each. First ball has a mass of 1.25 kg. What's the mass of the second ball?
Which ball has the velocity of 5?
Either one. It's up to you. Pick one. Now, since I have different masses, I'm going to say first ball, that's a box, but close enough. We're going to say that one has 5 meters per second. We're going to say that one has a 1.25 kg. That's the way I'll work it out. You could actually work it the other way, which I just realized that. Thank you for pointing that out. All right, while you are working on this, I'm going to send an email. Remember, vector, that momentum is a vector. That's your trick. How's it going? Any confusion yet, or anything I can help with? Here. All right, I'm gonna go ahead and write this up here in case I hadn't noticed it yet. One of them's positive, one of them's negative. Notice the two balls are moving in opposite directions. So I have to signify that over here. Positive direction, negative direction. I can make this one positive if I want. Alright, and I can make this one negative if I want, as long as they're different, right? As long as they're the opposite. So that means when I'm writing the after collision side, it's not after collision side, 1.25. And it said that each one of the balls move off in the opposite direction. So I can't just write 7.5 meters per second. Now my first ball is going negative 7.5 meters per second because it's going the opposite direction. Negative. Plus mass, and that's 7.5. So the whole trick of this one, quote unquote, is keeping your direction straight. If this one's positive, then this one has to be negative. If this one's positive, then this one has to be negative since it's now going the opposite direction according to the description. So when I start solving it, (1.25 times 5 is 7? I believe if I'm doing math.
6.25.
Is it 6.25? What am I doing with my life? 6.25. Oh, if it was 0.5, okay. All right. So now we just want to get all the m's on one side and all the not m's on another side. All right, let's go ahead and distribute out this negative sign here. Right. So I'm going to add 10 times m to both sides. So I got m 7.5 plus m 10 on the right, and I'm going to add 9.375 to both sides. So I got 6.25 plus 9.375. And what I did was I just got all of the m's on one side, sure, and all of the things without a variable on this side. Yeah. Plus n10 plus n10. That's just me adding it to both sides. And then I'm adding plus 9.375. I was like, oh no, my phone's ringing. Just for those of you who weren't sure, I just want to show you I'm adding M10 to both sides and adding 9.375 to both sides. That way I can get it in this order here. And if we're successful, this should come up with some values. We got 15.625 equals 17.5 m.
I messed it.
Say again?
Oh, let's see.
I did it wrong the first time, but I got it.
Okay. I was like, oh no, did I mess up? Not yet. Say again? Alright, let's make sure I'm not completely messing up.
I'm getting the same numbers, you know. I messed up on the maths.
With your statement, you got the same thing, Miss Kennedy. You're like, hey, I got that, or I got something different. I don't know why I can't hear today.
So we got to, I got here, this number instead of
Okay, let me. Yep, you're good, man. You're good.
But I did get the same answer.
Take care of your life. Let me make sure I didn't mess up somewhere. So that's 6.25. Let me make sure I got that from the right place. I got that by taking 5 times 1.25. So that was a 0.5 MV. So that was correct. And then that negative 3.75.
I think that's where I messed up. I think I might have doing the 1.5.
That might do it. Where I usually mess up here is the organization of my negatives, right? So being very careful, I'm going to rewrite it. Mass of the first ball, velocity of the first ball. The second ball is going in the opposite direction. So minus the mass of the second ball, velocity of the second ball. I put minus because they're going in opposite directions. You could just as easily put plus and then a negative here. I just went ahead and distributed out that minus sign. On the right side, this is after the collision. I've got the mass of the first ball. It's now moving off in the opposite direction, negative 7.5 meters per second. So if you want, you can put that negative out here, whatever makes you feel fine. Plus mass of the second ball, and this has the positive direction. I feel pretty good there. I then went through and just did some multiplication to clean it up a bit. This is where I came up with that 6.25 minus 10m, because I think that looks better. Negative 9.375, is that right? Or did I forget that already? That's all right. My calculator will save me. Thanks. I had just written it up on the board and forgot already. Okay, great. And now when I do these next steps, I'm going to do them one at a time instead of combining them. First, I will add 10m to both sides. I will then add 9.375 to both sides. And I'm doing that because I want to get my negatives positive if possible, right? I'm just trying to make it look better for me. I'm just trying to get everything on the same side, or everything with the variable on one side, everything without a variable on the other side.
9.375 negative.
1.25, so that's the mass of the first ball. The reason why that 7.5 is negative is because it says the balls move off in opposite directions. And what I meant that to mean is opposite directions of what they were going in the first place. So some problem with this question might have just been me and how I was writing it. So I'll try to make sure and clarify it for next semester. And from there, I think it all starts to fall out pretty nicely. Unless I look around like 5 times.
Racing goes.
No, I was just like, you can't see, I have like a giant, like, ridiculous smile on my face, like, what? I tend to be animated while teaching class because I know sometimes it can be super dry. And all right. And now we just got to divide both sides by 17.5. And that's where we get our answer of 0.89 kilograms. Awesome. That's super fun. I really enjoyed that. Okay. Now this one starts talking about things that are sticking together. And that's going to be a little different, yet I think slightly easier, because less information has to be given to us. So let's talk about this. And I really hope my microphone has been on the whole time. I'm going to check. Last week I was recording a video and my microphone was not on. It's turned itself off randomly. All right, we're good. We're recording. So now we're going to talk about a slightly different situation. Before we talk about a perfectly elastic collision, now we're going to talk about a perfectly inelastic collision. And in a perfectly inelastic collision, there's a lot of physics things happening, but the one that we are focusing on right now is the fact that the two objects are going to stick together after the impact. They stick together perfectly. As opposed to perfectly elastic where they hit each other and whoop. Now they're just going to be like, whoop. Or maybe even, whoop. Who knows? So now when I write before and after, we still got the same before. But now after, I only have one mass. And that one mass I have is the combined mass of both of them together. It's now one large object, right? With the mass of both of them put together. And since there's only one object, it can only have one velocity. And we're going to call the final velocity, right? So it's slightly different. If they stick together, then they have the same velocity after the impact. And of course, this mass here is this their total mass. I know you all were expecting some like large surprise on this one, but no, they just stick together. All right, what are we going to do with this? Well, like all of it, I can do example problems to see what would happen. Let's do one. All right. The diagram below shows two objects. This one has a mass of 3 kilograms. This one has a mass of 2 kilograms. After the collision, they stick together. And now we're going to calculate the velocities of the objects before or after. Whoops, the collision. No problem. Three kilograms, 4 meters per second. This one's going the opposite direction, so we can either write plus 2 times negative 2.5 meters per second, or we can just negative 2. Now, just from looking at this setup, you probably already have an idea of what direction they're going to be going after the impact. This one's more massive, and it's going faster. After the impact, more than likely, they're going to be going this direction. Seems right to me. Let's find out if we're correct. All right, they stick together. So here's their mass. And we just got to find their final velocity. Three times 4 is 12. 2 plus 5. Here. It's 7 divided by 5.
1.4.
What do you think? 1.4 meters per second? Finally using the I got something else option. Okay, well, I was glad to finally use the I got something else option. I was like, yay, you got something else. Right, well, yes. Well, one of the things about having set up like this is when you get an answer that's not on the list, you immediately think it's wrong and never really look at this one. All right, well, I'm not quite done with this problem. Really quickly, let's go back to the, do I want to do that one? No, I'll do that one later. Okay, let's just keep moving forward. We got a gun of mass that firing a bullet at a velocity of that, and the gun recoils with the speed of 14 meters per second. Calculate the mass of the bullet. Let me draw this. This is my 10-pound handgun I have here. Somebody's shooting. And when it fires the bullet comes out. Let me draw my handgun bullet. Oh. It's going at a rate of 320 meters per second. That one. And the gun recoils with the speed of 14 meters per second. That way. You gotta find the mass of the bullet. Can we do that? Yes, we can. How can we possibly do this? Well, let's think about something. All right. You're holding the gun in your hand. The bullet has not been fired. Is the bullet moving? Okay, the bullet is not moving. Interesting, interesting. Is the handgun moving? No, I mean, it's just in your hand, right? So that means that the sum of momentum is zero. Neither one of them are moving at first. So after you fired the bullet, the sum of momentum must still be zero. So here's how we can find out about that. The bullet momentum is going to be equal to the opposite of the gun momentum. All right? Because if we add these two together, then it should be zero. Awesome. So my gun momentum, let's say my gun goes backwards. 14 meters per second times 5 kilograms. Bullet 320 meters per second times m kilograms. So all we have to know for one like this is since they both start off not moving, the sum of the momentum has to equal zero. So after you fire it, the momentum must still be zero total. Therefore, the momentum of the bullet must equal the momentum of the gun. So I'm just going to solve for this mass here. I'm just going to solve for the mass. Say again? Ah. It can be, right? It can be negative. But when I'm doing this one, I was just like, it doesn't necessarily matter too much since I'm solving for the mass of it. Since I'm looking for some value that's always going to be positive, I can use absolute values for everything. Let's see. Let me try to see if I can find a different way to explain if that doesn't sound so hand-wavy and BS-y. There's not really a way to make it not sound like it's BS. I'm trying to think of another time where that works, and there is not one. That's a heavy. Okay, so this is obviously not a handgun. That was about 2.2 pounds.
Not even a rifle or something.
This is like I'm not a giant gun fan, but even I know enough to be like, this is not right. So the mass is about 0.22 kilograms, or 0.9 pounds. But look how heavy the gun is, though. All right, I'm going to stop trying to figure it out. The point of this one is we've got to set up, we've got to remember that the sum of the momentum equals zero. And since we are just looking for the mass of the bullet, I'm going to take the magnitude of the momentum of one object, set it equal to the magnitude of the other one, and then solve for the masses. Question on that part?
5.5 ton gun.
Okay. We got a few minutes left in class, so I want to talk about a few more things. We got a particle that explodes to become two particles. And it explodes. Okay. Now two particles. One of the particles goes off one way, the other particle goes off another way. This particle, which has 1 kilogram, velocity of 45 meters per second, this one has a mass of 2 kilograms and goes off at a different velocity. And it wants to know what, velocity does the other particle move. All right, so now that we're talking about velocities, we want to make sure and keep our negatives and stuff straight. You know that you got negative 2 times this velocity, if it's going the opposite direction, equals 1 times this one. So you can divide both sides by negative 2. So negative 22.5. Yes, this could be organized in a way to make that 22.5 positive, but on one like this, I would accept both answers. All right. Here's the questions I want you to take home with you in your heart or hand, notes. Which vehicle experiences the greatest force of impact? I got a large truck and a Volkswagen have a head-on collision. Nobody's in either one of them, so everybody's fine. We're just watching it. All right, so picture they hit each other. First question, which vehicle experiences the greatest force of impact? Think of Newton's third law. For every action, there's an equal and opposite reaction. Or if I put a certain force on you, you must put the same force back on me. So I ask you again, which one has the greatest force? Did someone say they're equal? I thought that's what I heard. It's the same, right? It has to be. If the truck pushed on the car with more force than the car pushed on the truck would just phase through the car, which is not something that happens in reality, right? They're interacting with each other. If this truck puts a force on the car must push back the same amount. But Mr. Palmer, what if the car can't push back the same amount? The car is going to slide backwards, or the structure will fail, right? But as long as they are in contact pushing against each other, this will hold true. Think of that. It's kind of counterintuitive. Which vehicle experiences the greatest impulse? What do you all think? The greatest change in momentum. I'm hearing answers. And I'm going to write this somewhere. Well, remember when we said the sum of the change in momentum equals 0? They have to be equal, right? P1 plus P must equal, change in P1 is going to equal negative change in P2. So their magnitudes are equal. Yes, the truck is bigger. Yes, this car is smaller. Their change in impulse is going to be the same. They interact with each other for the same amount of time with the same force. Their change in momentum must be the same. This is like a 10-point question on the test. I think on the test there's a bowling ball and a ping pong ball, then it's the same type of question. Their impulse must be the same. And in order for the way I remember this is by thinking, okay, what's changing this truck's momentum? Why would its momentum change? Well, it's changing because it hit this car. Okay, so we've got two objects. Momentum is conserved, which means if this car loses momentum, the truck must gain that amount of momentum and vice versa. Therefore, their change in momentum must be the same magnitude. Here's my second trick question in a row. Which one experiences the greatest momentum change? It's the same thing, right? Impulse is momentum change. They're the same values. They're the same thing, just people call them differently. And last but not least, which vehicle experiences the greatest acceleration? Now we can give the answer we want to give. We can say the car, right? Remember, change in momentum, M, the F minus the initial. This is of the truck equals negative M df, the initial, that's the car, right? Remember, the truck has a much larger mass. So in order for them to be equal, its change in velocity must be much lower. Since the car has a lower mass, its change in velocity must be higher. And of course, change in velocity over change in time is your acceleration. So the car has the greatest acceleration. Acceleration is not conserved, if that helps you any. So it can be different. All right, one last part of it. Well, you can just think of this. When fighting fires, a firefighter must use great caution to hold a hose that emits large amounts of water. Why would such a task be difficult? All right, so we've got this hose, and it is shooting water out. This water is coming out at a high velocity, which means it has a high momentum, right? This little nozzle that's coming out is shooting the water out, so it should have the same momentum, going in the opposite direction. But you'll notice that it's not moving. The reason it's not moving is because all these folks are holding it. So they are absorbing that momentum and basically transferring it into the ground. So it's hard to hold it because it's trying to like go flying backwards very quickly. Right? DT dubs, this is why you can fly spaceships in space. People are like, hey, there's no atmosphere to push off of. You don't need an atmosphere to push off of. The ship has a certain amount of momentum. If it ejects rocket fuel, that rocket fuel has momentum, which means the ship has to lose that much momentum or gain it in the opposite direction, right? When I learned that, I was like, mind blown. And then flown in space because that's something you can do because of momentum. Okay, well, I'll just be excited about it by myself. This one is one that you all can look at on your own. It's a trick question, so when you look at it, look for a trick. It says, consider a rail car of mass 500 kilograms coasting along a horizontal frictionless track, going this way. I'm going to drop a box of 100 kilograms from a height of 60 centimeters into the car, and your job is to find the final velocity. And I definitely want you to do this one on your own because it's hilarious. After maybe 5 minutes of working on it, you're just going to be like, was I just wasting my time? So look for some trick on it. I'm not going to tell you how to do it, but you can do it. Let me make sure the slide's up so you can Look at it on your own if you want. BT Dubs, this is where your test is going to pop up in case you didn't remember. Slides. Yes, it's there. So you have access to it. Just check it out at some point when you have a break. It's not really something you got to do for the test, but it's good to be able to see information that's not necessarily helpful. Let me put it back up on the screen. Track is frictionless. Velocity is yeah, you got it. Go for it. You all are dismissed. If you want to head out. Yay, fun class. I just can't hear today, though. Maybe my ears are stopped up.